Okay, so let's think about two reference frames. So one reference frame looks like this. So let's say this is X, this is Y. And we will consider another reference frame, the red reference frame, which looks like that. So clearly, here by design, we have y prime, which is equal to y, and x and x prime they can be different. So what I've drawn here is the situation where this prime coordinate system is moving at a constant velocity v to the right. And so v is constant. Constant velocity. Speaking about velocities, we already talked about the speed of light, c. Right? C is the value of 2.998 times 10 to the 8th power meter per second. So that's about let's say 600 million miles per hour. So it's an enormous speed. In the following, when we talk about velocity or speed, we will actually measure the velocity or speed in relative terms with respect to the speed of light. So when we write v, what we will actually mean is the value, the fraction of v over c. Okay, and so we have a name for this kind of unit system. It's called the natural unit system. In this natural unit system, we take c as the reference velocity, and by expressing all the velocities as a fraction of c, we are defining c as 1. Okay, so that's what I'm going to use for a while. All right, so so let's consider this this one reference frame and another reference frame, and we need to know how the coordinate system, how the coordinates can transfer between these two systems back and forth. What I'm going to consider is that suppose there's something happening, and then you're describing something that happens during some time interval delta t, and maybe during delta t some baseball travels 1 meter or something like that. So let's say there's a displacement in space, and in particular we will not be concerned too much about the displacements in the y direction or the z direction. We'll be concerned about the displacement in the x direction only. And the reason for that is because of this construction of these two coordinate systems. V is parallel to the x-axis, so y and z-axis. They're not going to be different between the two systems. They're going to be the same. So we are concerned about transformations of x and x prime and t of this reference system, inertial reference frame, and t prime of this primed inertial reference frame. So what we have in mind is that for some event that happens during a certain time duration and spatial duration, we have in mind that that's going to translate in this prime coordinate system, delta t prime and delta x prime. So the question that we ask is, what are the relationships between these two values, these two sets of values? Before I go further, let me actually make these delta t and delta x very, very small. Okay, very, very small. So technically I'm doing calculus, but there's no mystery to it. You just take delta t and delta x very, very small, so that so that you can write this thing as dt dx. And these two quantities can be written as dt prime, dtx prime. So it's the same sort of question. How does this set of values transform when you go from unprimed coordinate system to the prime coordinate system? And we're just concerned with very, very small displacements in time and space. And that's a good thing to do, because once you know how these quantities transform, you can use the integral calculus to learn what happens to any finite intervals of time and space. So this is a very good thing to do. Now, you can generally write this transformation as a linear relationship. Namely, you can write it as dt prime equals a dt plus b dx, and dx prime as c dt plus d dx. And why can you do that? What's the basis for doing that? Well, the reason why we can do that is because these dt's, dt primes, dx primes, are so small, so that any error that you introduce by ignoring so-called nonlinear terms, which are squares of dt's and dt times dx and so on and so forth, are completely negligible. Okay, so if you're good with multivariable calculus, what I have written down is nothing else than the chain rule of multivariable calculus. So, for example, A is what we call partial dt prime, partial t, and B is partial t prime, partial x, and so on and so forth. So C is partial x prime, partial t, and D is partial x prime, partial x. So this identity is a well-defined identity in differential calculus, and this is exact. Now, what we are talking about here is the small time interval dt and dx transforming to dt prime and dx prime. And there's this thing called homogeneity of time and homogeneity of space in physics. What that says is that physical laws are invariant over time, and physical laws are also invariant over space. In layman's term, what that means is that if Newton's law was valid yesterday, it's supposed to be valid today and tomorrow. And Newton's law is valid in New York, Newton's law is supposed to be valid in San Francisco too. What this means is that in the current context, these A, B, C, D, which determine the rule to transform these small time intervals and space intervals to the time intervals and space intervals in the other coordinate system, cannot depend on the choice of origins of time and space. What that means is that these A, B, C, D, they are basically independent of x and t. Because if they were, then depending on which part of space some baseball hitting event occurs, these transformation laws will be different, and that doesn't make sense based on this homogeneity of space and time. And so A, B, C, D are independent of x and t. And what else can they depend on? Well, notice that the defining number between this coordinate system and that coordinate system is this v, velocity v. So A, B, C, D must be a function of only one parameter, which is v. So A, B, C, D are functions of V. So now let's make some serious input to this structure. What we said was that if the speed of light is c in measured from one reference frame, then the speed of light is also c in the other reference frame. So let's consider light going to the right. So right-going light at the speed of light c. So what that means is that in terms of these dx's and dt's, remember that dx over dt is the speed of, that's the velocity. So we are assuming a right-going light. So that means this is participle c. But remember, c is now defined as 1 in my unit convention. So that means dx over dt is c. dt is 1. Okay, so if that's the case, then what it says is that Einstein's postulate says dx prime dt prime is also 1. Okay, so that means if dx is equals dt, then dx prime is also equal to dt. So let me put dx and dt to be equal in this equation. So that means dt prime equals, let me factor out dt, because dx is equal to dt, so you get a plus b. And in the second equation, you get dx prime equals dt c plus d, for assuming that we're describing a light moving event, a right moving light event. So now we have to use this second equation here. Dx prime is equal to dt. Dx prime is equal to dt prime. So that means these two are in fact equal. So what does that mean? So that means a plus b equals c plus d. Okay, so we got one equation there. So let's save it. Next, we consider another event which is similar to the event that another event that we consider is a left-going light. And if you do that, then what we can set is that dx dt is now -1, because the speed of light is c, but the direction should not change. The light is moving to the left at the speed of light, so the velocity is now -1. If that's the case, according to the postulate by Einstein, now we have to get the same thing for dx prime, dt prime. So that's also -1. So let's do the same thing, same manipulation here. dt prime in this case. Now dx is negative dt, so that means that dt a minus b. And then in the second equation, we can set dx prime equals dt c minus d. So now if you apply this thing here, which says that dx prime is equal to dx prime is negative dt prime, what we get is then a minus b equals negative of that, so d minus c. We get there. So these are the things that we were able to accomplish in the previous page. So these are the transformations. These are the equations that we got for the coefficients, and this diagram defines the inertial reference frames. So now let's solve this set of equations. So what we will do, we will regard A and B as given, and we will actually solve for C and D. Okay, so that's one strategy. So you can add these two equations up, and then the left-hand side will become 2A, right-hand side will become 2D. So what that means is D equals A. You can also subtract these equations, and then you get 2B equals 2c. So that means c equals b. Okay, so those are the answers. Those are the solutions of this set of equations. We have one more observation we can make. The observation is that suppose that for example, you observe the origin of this red coordinate system, or any other fixed point in the primed reference system. By definition, that point must be moving at velocity v when it's observed from the unprimed reference frame here, because, well, we said that this reference frame is moving at velocity v with respect to the unprimed coordinate system. So what we mean by that is that if dx prime is 0, it's a fixed point in the prime coordinate system, it must be that dx dt is v, because that's the specification here. So if that's the case, then we can figure out the relationship between c and d, or a and b here. So if dx prime is 0, so then what we get is c dt equals negative d dx. So dx dt is equals v, so that means let's divide both sides by dt, so that means negative d dx dt. So that means c equals negative d v. So that means in terms of a and b, this is b and d equals a, so that means b equals av. So then we can rewrite these coordinate transformations as the following. So dt prime equals a dt minus v dx, and dx prime equals c is equal to b, and d equals a. So let me factor out a here. A v dt, hold on a second, negative v dt plus dx. So now we got these. So we get almost the final result for what's called a Lorentz transformation. Now let's write dx dt, hold on a second, dt dx as a function of dt prime and dx prime. So if you know a little bit of linear algebra, you can say, well, I can just invert these relationships. Well, that's possible, but let's do something else here. The relationship between the prime coordinate and unprimed coordinate is basically, if you relative to the prime coordinate, the unprimed coordinate is moving at the speed which is negative v, right? And we know that there is no such thing as absolute velocity. So then it must be that the coordinate transformation is given by this. Just replace v with negative v, because the unprimed coordinate has the relative velocity of negative v with respect to the primed coordinate system. So then we have also a here, but this a, let's recall that this a is a function of velocity. So that means it's a function of negative v here, whereas in these formulas, this a value was a function evaluated at velocity v. So these two values are to be distinguished for the time being, at least. Now we will argue that this a is in fact it has the same value if it's v or if it's negative v. And why is that? Well, it's from the following argument. So what is the physical meaning of AV or A negative V? So imagine that you have a clock. You have a clock. Let me use the red color. You have a clock fixed at the origin of this prime coordinate, and then this clock is moving at the speed of v because it's fixed at the origin of the red coordinate system. So in that case, for the clock ticking event, dx prime will be 0. A clock fixed at any point in the prime coordinate system, dx prime is 0. So then dt is given by a negative v over dt prime. What it says is that if the clock ticks, let's say 1 second every second here, when you see the same event, clock ticking event in the unprime coordinate, so when you're watching a moving clock, it ticks at a different rate. So it's a time scale changing factor, which is what this a negative v is. By the same reasoning, this a is also the time scale changing factor, except that it regards the time scale change when you're watching a clock moving at negative v instead of a positive v, because now here what you're in order to get this formula, you will set dx equals 0. So if you do that, then that clock from the prime coordinate point of view is moving at negative v. So AV corresponds to clock moving at negative v, and this is this corresponds to clock moving at positive v. But if a clock moving at positive v looks to go, in fact the correct answer is it goes slower. So if it goes at a slower rate, then do we have any reason to believe that if the clock is moving in the opposite direction, should it go at a different rate? The answer is no. Why? Because the space, there's no reason to distinguish any directions in space as far as we know. So clock, in fact, clock moving in any direction if it goes at a different, if it observed to go at a different rate than the clock at rest, then it should go, it should be, the rate change should be independent of the direction in which the clock is moving. So in a fancy language, that's what we call isotropy of space. The physical laws should be independent of all the directions of space, isotropy of space. And therefore, AV is equal to A minus V. So with that crucial fact explained, so I replaced these symbols with just A's because they are the same quantities. So I proved that these A's depend only on speed, only on the magnitude of the velocity, not the directions. So now what I'm going to do is these two sets of equations can be manipulated further in the following way. So let me actually just use this dt prime on the right hand side and use that dx prime on the right hand side. So what I get is then so dt equals a dt prime, but that's a dt minus v dx, so that there's another factor of a, so I'll take it out, and so what I get is then dt minus v dx, And then v dx prime, so dx prime is there, so then I multiply this one with v, and I have already taken out a, so that just multiply v here, so that means this becomes negative v squared dt plus v dx. Aha! You can see that this guy and that guy cancel out, so what you get is 1 minus v a squared 1 minus v squared dt. So this is dt equals something times dt, so that means that this must be 1, and therefore a is in principle plus minus 1 minus v squared. But as we said, a has the meaning of time going slow or faster, depending on whether the clock is moving or not moving. It would be really surprising if the clock was moving backwards just because it was moving. You can't just reverse the time by having the clock moving. And so the negative sign is unphysical. So we choose the positive sign. The negative sign is an unphysical solution. So then a is 1 over 1 minus v squared, square root of that. And so this is what we commonly refer to as gamma in the special relativity literature.